Hi students, welcome to AIM Teachers Tech. So today we'll see the equations of DFT and IDFT. What are the main equations and what you have to remember. Okay, so I hope you know what is DFT now, full form of DFT. Last video I have told you what is DFT. So it is discrete Fourier transform. Fourier transform is a process, or you can call it as a technique to convert a signal from time domain, that is discrete signal from time domain to frequency domain. Okay, so if you see here, this is your x of n discrete signal. Now if you take a Fourier transform of this, it is nothing but DFT of x of n. So DFT of x of n, in the sense it is nothing but we are representing as x of k. How we are representing? We are representing as x of k. Now we'll define the range of this n. N is defined as, that is 0, 1, dash 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 n minus 1. I can write like this, or even I can write like this, greater than or equal to 0, less than or equal to n minus 1. Both way I can write, both are same. So k also, it has been defined, the range of k is also k and n range will be always equal. Here we are taking for the positive value, so 0, 1, dash 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 n minus 1. Okay, now this one is in time domain, that is nothing but your n. N is defined in time domain, and k, this one k is defined, this is in frequency domain. So we are taking k in frequency domain, and I hope everyone knows what is n. N is number of sample. So when we convert from analog to digital, that is we do sampling, at that time the number of samples we take is here, this one, these are the number of samples here, these are the number of samples, this one are the number of samples. Okay, let us consider a discrete signal x of n. Let us consider a discrete signal x of n, that is of finite length, which is of finite length, finite duration of length, equal to n, that is n, n is greater than or equal to 0, less than or equal to n minus 1. Okay, so then the n point DFT, then n point, see we are taking n samples, so how do we call it as? For n samples we are calling it as n point DFT x of n is defined as follows. So how do we write this equation? We write equation as DFT, open the bracket, x of n is equal to, so how do I write this one? DFT of x of n. That means after taking DFT of x of n, so the notation becomes x of k, that is it is into frequency domain. So by definition, how can I write this? Summation n is equal to 0 to n minus 1, okay, x of n e to the power of minus j k omega n. Okay, so this one you take down as equation 1, where k is equal to, n is defined here, so we will define the range of k. So k is equal to 0, 1, dash dash n minus 1. Okay, so similarly I can write the equation for IDFT. IDFT is equal to, whose IDFT we will take? We will take IDFT which is there in, that is we are converting, IDFT means we are converting back from frequency domain to time domain. So we have to take as x of k. We are converting back from frequency domain to time domain. Okay, so the what is the value here? Here the value is x of k. So this is equal to, once I take a DFT, IDFT of x of k, that means we are converting from frequency domain to time domain. So time domain signal is what? X of n. So this is by definition, how many samples? We have n number of samples, so it is 1 by n summation k is equal to, as input is what here? Input is x of k. We are doing on x of k, so the range is k, so this becomes k here. So k is equal to 0 to n minus 1, n minus 1. So inverse of this value, so it is e to the power of plus j k omega n. So this one is your equation 2. So already k we have defined here, so we will define here n. So n is equal to 0 comma 1 comma dash 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 n minus 1. Okay, so in DFT analysis, n is known as this n, capital N is known as transform length. Yes, now let us sample x of k in the range of that is in the range of 0 to 2 pi. So the sampling interval, will be equal to how much? It is 2 pi by n. So this I have already explained in my last video. So that's why omega, what will be the value of omega? Omega will be equal to 2 pi by n. In substituting the value of omega in equation 1 and equation 2. So the equation was DFT open the bracket x of n by this, so this will be equal to x of k. So by definition, so this is equal to summation n is equal to 0 to n minus 1. So on which signal we are doing? We are doing on this signal DFT. So it is x of n e to the power of minus j 2 pi by n kn. So this one we will take it as equation 3. Okay, same way we will substitute in equation 2. So that is IDFT open the bracket. So this is done on frequency domain signal, that is x of k. So if we take a IDFT of this, so the signal will be x of n. So by definition, so this will be equal to 1 by n summation k is equal to 0. So the input is x of k e to the power of plus j 2 pi by n kn. So we have substituted the value of omega, that is 2 pi by n. So this equation will be equation 4. Now the equation 3 is known as endpoint DFT. This equation, that is equation 3, is known as endpoint DFT analysis equation. Okay. So now let us, so this one, if you see the sampling theorem, equation 3 is equal to this, and the sampling theorem and reconstruction we have done, no? Reconstruction equation 6 is equal to this. Okay. So only for x of k, there we have taken as x of 2 pi by n into k we have taken there. But here we have taken as x of k. That's all is the difference. And for x of n, there we have taken as xp of n. So if you want, you can compare both the equations are said in last derivation. What we have done, the equation 3, which one I have told you, DFT equation. So this is also a DFT equation, so this is equal to that. and the equation 6, which is there in your reconstruction of your frequency domain sampling, so that one is equal to this equation. Okay, fine. Let omega n, we will define one term called as omega n, be the complex basis function, basis, which is defined as omega n is defined as e to the power of minus j 2 pi by n. So this is called as, omega n is called as phase factor, or it is also called as twiddle factor. Now this twiddle factor, that is omega n, this one I'm going to substitute in equation 3 and 4. The equation 3 becomes DFT, open the bracket, x of n, close the bracket. So this will be equal to x of k. So by definition we have written as summation 0 to n minus 1. Input signal is what? X of n. See here, this one, e to the power of, there it was e to the power of, this whole thing I'm going to substitute as omega n, that is twiddle factor. So this becomes omega n kn. So kn is not there here, kn is left. So you can see here you have a kn here. You have a kn here. Can you see this kn? So this whole part I'm going to substitute as what? Omega n. Okay, fine. So this becomes my equation 5, and I'm going to define the range of k. So 0, 1, n minus 1. Okay. So next I can, same way I can write the equation of IDFT. Close the bracket, x of k. Okay, so what is this? If I take a IDFT of x of k, so what I'm going to get it as x of n. So by definition, so this is equal to summation k is equal to 0, n minus 1. So this is x of k into omega n. See here you have a minus here, but in this equation there is no minus. So this becomes minus kn. And this equation we are taking as equation 6. So this is k we have defined already. K we have defined here. So what we have to define? We have to define n is equal to 0, 1 dash n minus 1. So these are the two equations mainly you have to remember. These are the DFT equations. These equations are with respect to twiddle factor. So this is with respect to twiddle factor. These two equations of IDFT and DFT you have to remember, and this equation is also you have to remember. These two equations are with respect to e to the power of. Okay, so somewhere we are going to use twiddle factor equations, and somewhere we are going to use these two. Remember, both the equations are same only. So equation 3 is almost it is equal to equation 5, and equation 4 is equal to equation 6. Only the difference is this part we have taken as e to the power of minus j 2 pi by n, we have taken as omega n, and we have substituted this. That is, we are calling it as a twiddle factor or phase factor. Okay, so that's all. So thank you for watching this video. We'll meet again in the next video. Subscribe, please subscribe, share.